want to talk about the rate of effusion in this video. Now, in order to understand rate of effusion, or the rate at which gases effuse, we need to understand what gaseous diffusion is. Now, gaseous diffusion is a process in which one gas is spread through another gas evenly and uniformly. Given a sufficient amount of time, and due to the chaotic motion of molecules, now think the kinetic molecular theory of gases, it will result in the complete mixing of gases. So given a sufficient amount of time, just due to the chaotic random nature of molecules, eventually two gases will mix together uniformly and evenly. This is just a natural occurring phenomenon. Now, this process will happen quicker at higher temperatures, and this should make sense because molecules are moving at faster rates at higher temperatures, because when there are higher temperatures, the gases will have more kinetic energy and they'll move quicker. Now, effusion is like diffusion in that it involves the flow of gases, but it's actually simpler. So what I want you to do is I want you to imagine a container of gas. This container is placed inside of a vacuum. Then a small hole is formed in the side of the container. And through the small hole, gases will escape from the container into the vacuum. And the process that I've just described to you is the process of effusion. Now, if we look at these two images here, we've got gases effusing through this small hole. Now, of course, the larger the hole, the faster the rate that gases will be allowed to effuse. Remember, when gases are inside of a container and they have kinetic energy associated with them, so there's kinetic energy associated with these gases, and they move around this container. Now, as they bounce around this container, eventually one of these gas molecules will pass through this hole. So obviously, if the hole is larger, the gas molecules will effuse quicker out of the container. Now, Thomas Graham was the one who studied this process, and in 1846, he discovered the rate of gaseous effusion is inversely proportional to the square root of the gas's density. Now, when we state Graham's law of effusion, we like to state it in terms of molecular weight. So, in other words, the rate of effusion of a gas is inversely proportional to the square root of its molecular weight. So the rate at which a gas effuses from a container or through a hole, it is inversely proportional to the molecular weight. So the rate of effusion is equal to 1 over the square root of the molecular weight of that gas. Now, if you compare the effusion of two gases from the same container at the same temperature and pressure, their effusion rates are given by the inverse ratio of the square roots of the masses of the molecular particles. So this equation would be as follows. So if you wanted to compare the rate at which gas 1 effuses to the rate at which gas 2 effuses, this would be equal to the square root of the molecular weight of gas 2 divided by the molecular weight of gas 1. So whichever gas that you have on the top, on the left-hand side of this expression, it will go on the bottom of the right-hand side of this expression. And so since gas 2 is on the bottom, it will go on the top in this side of the expression. Let's do an example now. If the rate of effusion for an unknown gas is twice that of O2, determine the molecular weight of the unknown gas. If you'll recall, Graham's law says that the rate of effusion of gas 1 compared to the rate of effusion of gas 2 is equal to the square root of the molecular weight of gas 2 divided by the molecular weight of gas 1. So we can rewrite this expression as the rate of effusion of the unknown gas compared to the rate of effusion of O2 is equal to the square root of the molecular weight of O2 divided by the molecular weight of the unknown gas. So we can rewrite this expression here. So in the problem statement, it says the rate of effusion for unknown gas is twice that of O2. So 2 to 1, because the rate of effusion for our unknown gas is twice that of the rate of effusion of O2, is equal to the square root of the molecular weight of O2, which from the periodic table we see as 32 grams per mole divided by X. Square both sides of this expression, bring X over to this side of the equation, and we see 4X is equal to 32 grams per mole. Divide both sides by 4, and we see that X is equal to 8 grams per mole. Therefore, the molecular weight of our unknown gas is 8 grams per mole.